Okay, so we're going to look at another example of integrating using inverse trig functions. Um, but again, this one is a little bit more sophisticated than some of the earlier examples. Um, what I'm going to notice here about this integrand is that it's really close to being able to integrate this using the natural log function, right? Because what you have here is almost, but not quite, the derivative of the denominator in the numerator, right? See, here you have this expression in the denominator, x squared plus 4x plus 5. And if you take the derivative of x squared plus 4x plus 5, of course you get 2x plus 4, which is almost what we have in the numerator. So we could almost integrate this, almost, but not quite, integrate this using the natural log function, right? So I'm going to play a little algebraic game here, or a little arithmetic game in this example. What I'm going to do is uh, make the problem look slightly different, but it'll be equivalent. So I really haven't changed it. But I'm going to make it look different. And the way I'm going to do that is by adding 1 into the numerator and then immediately subtracting the 1 back out. Okay. Now at first that looks like a completely absurd thing to do, right? Just add 1 and subtract 1 in the numerator. Of course, 1 minus 1 is 0, so we haven't changed the integrand at all. But here's why that's beneficial. Because if I group the 3 and the 1 together now, then I've made the integrand look different. I have 2x plus 4 minus 1 in the numerator, and then again the x squared plus the 4x plus 5 in the denominator. And the reason that's nice now is because notice the 2x plus 4 is the derivative of the denominator, x squared plus 4x plus 5. So if I didn't have the minus 1 here, I would be able to integrate this integrand using the natural log function. So guess what I'm going to do? I'm going to just get rid of the minus 1. And the way I do that is by breaking up this integrand into two separate terms. And then I'm going to try to integrate those two terms separately. So I have 2x plus 4 over x squared plus 4x plus 5, minus 1 over x squared plus 4x plus 5. And now, like I did in the previous example, I'm going to integrate those two terms separately. So I'm going to integrate the 2x plus 4 over the x squared plus 4x plus 5. And then I'm going to integrate the 1 over the x squared plus 4x plus 5. So I'm kind of using a divide and conquer strategy here, and I'm hoping that the two separate integrals will be easier to integrate than the original integral. And actually, that turns out to be the case. That does turn out to be the case here, because, let me add a little paper. Notice that the, let me add some paper as I said there. Notice now that this is the reason why I added and subtracted the 1 to begin with. Notice now in this first integrand, you have this expression in the denominator, x squared plus 4x plus 5, and its derivative is in the numerator, right? So you have the derivative of an expression divided by the expression, and you know now that you can integrate that using natural log, right? That's the perfect setup for natural log. So the antiderivative of 2x plus 4 over x squared plus 4x plus 5 is just going to be the natural log of the absolute value of x squared plus 4x plus 5. So you can try using substitution if you want to, letting u be x squared plus 4x plus 5. And when you go through that substitution, you will indeed come up with the antiderivative being the natural log of the absolute value of x squared plus 4x plus 5. I just skipped the substitution step because it was sort of obvious here that we had the derivative of the denominator in the numerator, right? All right, now that's the first integral. Now what about the second integral? We're not going to be able to integrate this using natural log, but I'm going to integrate this using my completing the square technique. So I'm going to try to complete the square on this quadratic expression in the denominator, and then I'm going to see if I can apply one of the inverse trig functions to integrate. All right, so let's try completing the square on x squared plus 4x plus 5. So that's fairly easy to do. Remember, we're going to complete the square on the x squared plus 4x part of the denominator, and then let's see what happens to the 5 as we go through that process. So to complete the square on x squared plus 4x, remember you take the coefficient of the x term there, which is 4. You divide that by 2, and then you square that. And of course, that's going to become positive 4. So I'm going to add now a positive 4 into my set of parentheses here, the grouping that I created in that denominator. But since I'm adding 4, then I have to remember to undo that addition of 4. So outside of the parentheses, I'm going to subtract 4. 4 minus 4, of course, is 0, so we really haven't changed the denominator at all. It's still x squared plus 4x plus 5, but now we made it look different. And the reason it's convenient that we made it look different is now I can write that set of parentheses as a perfect square, right? So I have the integral of 1 over, and how does x squared plus 4x plus 4 factor? It's going to factor as x plus 2 squared. Just check that if you don't believe me. And then, of course, plus 5 minus 4 is plus 1, which we can write as 1 squared. So here we have an expression squared plus a constant squared, right? 1 over that. And so we know that we can integrate that using the arctangent function. In this case, my u is going to be x plus 2, and the a, of course, is going to be 1. So you can make the substitutions if you like, but in the end, this integrates as 1 over a, right, 1 over 1, times the arctangent of u, which is x plus 2, over a, which is 1, right? And then, of course, don't forget, for both of these integrals, we need to add that arbitrary constant c. So here's we're done, all right? See, our divide and conquer strategy worked nicely here, breaking that integrand up in just the right way into two separate terms allows us to find the antiderivative for the original integrand. There it is. So it's a ugly looking antiderivative, but we have it.